Alright, welcome to yet another lecture. And in this lecture, we are going to talk about something honestly very exciting in modern system design. Real-time APIs. Now, before we get technical, just think for a second about the products you personally consider world-class. Maybe tools like Figma, where multiple designers can edit the same design file at the exact same time. Or Slack, where messages appear instantly the moment somebody sends them. Or Google Docs, where you can literally see another person's cursor moving live while they type. Even trading platforms, where stock prices update every few milliseconds in real time. Now here's the important thing. None of these experiences are built using traditional HTTP request response alone. HTTP, Hypertext Transfer Protocol, normally works in a very simple way. The client asks for something, and the server responds. This is called a pull model. The client keeps asking, anything new? Anything new? Anything new? And honestly, for real-time systems, that becomes inefficient very quickly because users don't want updates every few seconds. They want updates immediately, the moment something changes. So for these kinds of applications, we need something different. We need a push model, meaning instead of waiting for the client to ask, the server itself pushes data to the client the instant something changes. That's how real-time systems feel fast and alive. And this is exactly the problem solved by technologies like WebSockets, server-sent events, often called SSE, long polling, and gRPC streaming. gRPC meaning Google Remote Procedure Call. Each of these technologies solves the real-time communication problem, but in slightly different ways. Different trade-offs, different strengths, different use cases. So by the end of this lecture, you are going to understand how these technologies actually work under the hood, when to use each one, how real companies build real-time systems at scale, and also what usually goes wrong in real-time architectures, because honestly, many things can go wrong there, and of course, how to prevent those problems. And personally, I think this is one of the most satisfying parts of system design to learn, because unlike some back-end concepts that stay invisible, real-time systems are immediately visible to users. When a real-time feature works well, users instantly feel it. The product feels modern, responsive, alive. And honestly, that feeling is pretty amazing when you build it yourself. So yeah, let us begin. Before we look at the solutions, I want to make sure you fully understand the problem. Because naively, solving real-time with HTTP polling is something almost every developer does the first time they try it. And it is expensive in ways that are not obvious until you hit scale. Look at the diagram on the left. This is naive polling. A client wants to show new messages as they arrive. So it asks the server every second, any new messages? The server says no. The client asks again. No. Again, no. This continues until a message actually arrives. In a quiet period, which is most of the time, 99% of those requests are pure waste. The server processes them. The client waits for a response. The connection is opened and closed. Nothing useful happens. Now look at the 4 problems on the right. Latency. If you poll once per second, the worst case latency for message delivery is 1 full second. In a chat application, that is noticeable. In a collaborative document, it is infuriating. In a trading platform, it is catastrophic. Bandwidth waste. Every HTTP request sends headers. A typical HTTP request header is 500 bytes. At 100 clients polling once per second, that is 50 kilobytes per second of pure header overhead, carrying no useful data. At 10,000 clients, it is 5 megabytes per second. You are paying for bandwidth that does zero useful work. Server load. The number of requests your server handles scales with the number of clients, not with the amount of activity. During a quiet period at 3 a.m., your server is still processing millions of polls per hour. From clients checking for messages that do not exist. Battery drain. On mobile, every network request wakes the radio. Every poll keeps the CPU active. Constant polling is one of the fastest ways to drain a phone battery. This is why Apple and Google built push notification systems to replace polling with server-initiated delivery. These 4 problems are why HTTP polling does not work for real-time use cases. And understanding these problems is exactly why WebSocket, SSE, and long polling were invented. WebSocket is the core real-time solution, and it works by upgrading a normal HTTP connection. It starts as a standard HTTP request, passes through firewalls and proxies, and includes an upgrade WebSocket header. The server replies with HTTP 101 switching protocols, upgrading the connection into a persistent TCP channel. From there, both client and server can send messages anytime. No polling, no reconnects per message, just continuous two-way communication. This results in very low latency, usually just a few milliseconds, compared to polling, which can introduce delays of hundreds or even thousands of milliseconds. Key properties: full duplex, both sides can send and receive at the same time. Persistent connection, no repeated TCP handshakes, so far more efficient. Supports text and binary frames. JSON, events, or binary data can all travel on the same channel. Native browser support, built into all modern browsers via window.websocket, no libraries required. Sub-protocol support, WebSocket handles transport, while protocols like STOMP or MQTT define messaging structure on top. Alright, so let's talk about something very important in real-time systems. WebSocket is powerful, actually the most capable real-time technology we have in the browser. But here's the key idea: it is not always the right choice. Sometimes you need something simpler. And that's where server-sent events and long polling come in. So first, server-sent events, SSE. Now this is one of those technologies that honestly a lot of engineers overlook, which is surprising because it is actually built into every modern browser. No extra libraries, no special setup, and it solves a very specific problem really well: server-to-client updates. Now here is the most important constraint you need to understand. SSE is one-way only. Let me repeat that. One-way only. So the server can push data to the client, but the client cannot send data back through the same SSE connection. So it is not bidirectional like WebSocket? Now you might think, isn't that a limitation? And yes, sometimes it is. But for many real-world use cases, it is not a limitation at all. Think about notification feeds, live dashboards, news tickers, score updates. In all of these cases, the client is mostly just listening. The server is the one sending updates. So SSE fits perfectly. Now here is why SSE is actually very attractive in production. First, it is just HTTP, plain HTTP, which means it works through almost everything: proxies, CDNs, firewalls, enterprise networks. No special upgrade handshake, no custom protocol layer, just standard HTTP streaming. Second, it has automatic reconnection built in. So if the connection drops, the browser automatically reconnects. And it can even resume from where it left off, using something called last event ID. That means you don't lose events easily. Very useful for reliability. And just to make this concrete, even modern AI streaming systems use SSE. For example, when you see responses streaming word by word in tools like ChatGPT, that is server-sent events. Each token, each small piece of text is delivered as an SSE event. Simple, clean, and very efficient for one-way streaming. Now let's talk about the second option, long polling. And honestly, this is like the fallback of fallbacks. It is older, but still very useful in some environments. So how does it work? The client sends a normal HTTP request, but the server does not respond immediately. Instead, it holds the connection open, maybe for 10 seconds, 30 seconds, sometimes longer, until there is something to send. Once data is available, the server responds. Then the client immediately sends another request again, and this cycle repeats. So it kind of simulates real-time behavior using normal HTTP, so by Morse code. Now the big advantage here is compatibility. It works with absolutely any HTTP client. No special browser APIs, no protocol upgrades, no WebSocket support required. So if you are dealing with legacy enterprise systems, old proxies, restricted environments, long polling is often your only reliable option. But of course, there is a trade-off. It is more expensive because every message involves a full HTTP request. Headers, connection setup, overhead, all of it repeats. So compared to SSE or WebSocket, it is less efficient. So if you step back and compare everything, the idea becomes very clear. WebSocket is the most powerful and flexible. SSE is the simplest and most elegant for one-way streaming. And long polling is the most compatible fallback when nothing else works. And in real systems, you often end up using a combination of all three depending on constraints. Alright, so now let's put all four real-time technologies side by side so you can directly compare them and really internalize the differences. And honestly, this is where things start to click properly. So first dimension, direction of communication. WebSocket, long polling, and gRPC streaming, all of these are full duplex, meaning both client and server can send data to each other freely. Now SSE, as server-sent events, is different. It is one way only, server to client. So if your system needs the client to constantly send data back, like mouse movements in a collaborative editor or real-time game inputs, then SSE is not suitable as your main channel. That's a very important limitation. Now, second dimension, latency. WebSocket and gRPC streaming are the fastest here. We are talking roughly 1 to 5 milliseconds on good networks. Very low latency, very responsive. SSE is slightly slower, mainly because it runs over standard HTTP and has some overhead. And long polling is the slowest, because it depends on how often you poll. So latency can range from about 50 milliseconds all the way up to 500 milliseconds, sometimes even more, depending on your interval. Now, third dimension, browser support. WebSocket and SSE are both natively supported in all modern browsers, so you can use them directly without extra complexity. Long polling is universal, because it is just normal HTTP requests, so it works anywhere. Now, gRPC streaming is a bit different. In browsers, you cannot use it directly. You need something called gRPC-web, which basically means a proxy layer sitting between the browser and your backend services. So there is extra infrastructure involved. Now, fourth dimension, auto-reconnect behavior. This is actually very important in production systems. SSE has built-in reconnection, meaning if the connection drops, the browser automatically reconnects and can even resume where it left off. Very convenient. WebSocket and gRPC streaming do not have this built in. You need to implement reconnection logic yourself, including retry handling, backoff, all of that. Now long polling kind of reconnects naturally, because every request is independent, so when one request finishes, the client just sends another one. So it behaves like continuous polling automatically. Now, fifth dimension, mobile battery usage. And this is something people often forget. Long polling is actually the worst here, because it constantly creates new network requests, which wakes up the radio frequently and drains battery. WebSocket, SSE, and gRPC streaming all maintain a persistent connection. So fewer wake-ups, better battery efficiency overall. That's a real production consideration for mobile apps. Now finally, let's summarize use cases. This is the most important part. WebSocket is best for chat systems, multiplayer games, and real-time collaboration, where both sides need to send data continuously. SSE is best for feeds, dashboards, notifications, and AI streaming, where the server mainly pushes updates. Long polling is best for legacy systems or as a fallback when modern connections fail. And gRPC streaming is best for internal microservice-to-microservice communication, where performance and type safety matter the most. So if you step back and look at everything together, the key idea is simple. There is no best real-time technology, only the right tool for the right communication pattern. And once you start thinking like this, real-time system design becomes much more intuitive. Alright, so now let me show you something really interesting. Let's look at how 4 of the best real-time products in the world actually build their real-time features in production. And honestly, each one teaches you a slightly different lesson. First, Figma. Figma is probably one of the most impressive real-time systems ever built. Because think about it, you move an object on your screen, and your teammate sees it move instantly on their screen. No refresh, no delay, just real-time synchronization. And yes, under the hood, this is powered by WebSockets. Every single action, mouse movements, shape edits, text changes, they all become WebSocket events and are broadcast to other connected users in the same file. But here's the key engineering insight from Figma. And this is very important. The WebSocket connection itself is actually the easy part. The hard part is not transport. The hard part is conflict resolution. Meaning, what happens when two people edit the same thing at the same time? Who wins? What gets merged? What gets overwritten? To solve this, Figma uses something called operational transformation. Operational transform basically means instead of just sending changes directly, the system transforms edits so they do not conflict incorrectly. So one user sends changes, another user sends changes, and the system intelligently merges them. So the lesson is very clear. WebSocket moves the data, but algorithms decide correctness. Now, second example, Slack. Slack uses WebSocket for its real-time messaging system. This is called the Real-Time Messaging API. So messages appear instantly as you send them, but here is something very important. Slack does not rely only on WebSockets. They always implement a fallback using long polling. Why? Because in real enterprise environments, corporate networks are complicated. Many companies use HTTP proxies that block or modify WebSocket upgrade headers. So in those environments, WebSockets simply fail. So Slack's lesson is very practical. Never assume WebSocket will always work. Always provide a fallback like long polling so your system works everywhere. Reliability matters more than elegance. Now, third example, Robinhood. Robinhood uses real-time streaming for stock prices and trading data. But interestingly, they don't always use the same protocol everywhere. On mobile apps, they typically use WebSockets because mobile apps need more interactive communication. But on web dashboards, they often use server-sent events SSE because price updates are mostly one-way, server to client. So the lesson here is very important. You do not need to standardize on one real-time protocol. Different clients, different constraints, different choices. Mobile and web can and often should use different technologies. Now, final example, ChatGPT streaming. When you see responses streaming word by word into your screen, that is server-sent events SSE. Each token, each small piece of text is sent as an event. The browser receives it and renders it immediately. No WebSocket needed, because the data flow is completely one-way. The model generates, the client displays. That's it. And this is actually why SSE became so popular again recently, because AI streaming made it extremely visible in real-world applications. So if you step back and look at all four examples, you will notice a pattern. Real-time systems are not about choosing one perfect technology. They are about matching the right tool to the right communication pattern and understanding what problem you are actually solving. That's the real engineering skill here. Alright, so now let's talk about something very important and honestly a bit advanced. Because building a WebSocket proof of concept is actually quite easy. But scaling WebSockets to something like 1 million concurrent connections, that's where things get really serious. That becomes a distributed systems problem. So let's break it down slowly, step by step. First, understand the baseline. A single WebSocket server in a normal setup can handle roughly around 50,000 concurrent connections. And that limit is not random. It comes from things like file descriptor limits, memory usage per connection, CPU overhead, and network pressure. So eventually, the server just starts struggling. Now imagine you need 1 million concurrent users. Simple math, you need at least 20 servers, maybe more depending on traffic patterns. But the moment you go beyond one server, everything becomes more complex. Because now your system is distributed, and distributed systems always introduce new problems. So let's go through those problems one by one. First problem, sticky sessions. So WebSocket connections are stateful, meaning once a user connects to a server, they stay connected to that exact server. They don't randomly switch. So if a client connects to server 1, all their messages must keep going to server 1. Now the issue is normal load balancers, like simple round-robin ones, don't understand this. They just distribute traffic randomly, which breaks WebSockets completely. So what do? We enable sticky sessions. Sticky sessions basically mean once a user is assigned to a server, keep sending them to the same server. This can be done using IP hashing, cookies, or session affinity. Or alternatively, you use managed solutions like socket.io or services like Pusher or even cloud-managed WebSocket gateways like AWS API Gateway WebSockets. These handle connection routing complexity for you. Now, second problem, cross-server message delivery. This one is very important. Let's say user A is connected to server 1. User B is connected to server 2. Now A sends a message to B. So server 1 receives the message, fine. But user B is on server 2. And server 2 has no idea that this message even exists. So without coordination, the message just gets lost. So how do we solve this? We introduce a message bus or pub sub system. Pub sub means publish and subscribe. A very common solution here is Redis pub/sub. So what happens is server 1 publishes the message to Redis, and server 2, which is subscribed, receives it instantly. Then server 2 delivers it to user B. So now servers can communicate indirectly. Third problem, connection management at scale. Now this is where things get heavy. 1 million connections means 1 million TCP connections, 1 million open file descriptors, and memory usage per connection. So you cannot treat this casually. You need proper horizontal scaling. You need connection pooling strategies, and you need heartbeat mechanisms. Heartbeat basically means, are you still alive? If not, clean up the connection. Otherwise, you slowly leak resources. Now, fourth problem, and this one is very real in production. Reconnection storms. So imagine this. One server restarts. Now suddenly, 50,000 clients get disconnected at the same time, and all of them try to reconnect immediately. At the exact same second, that creates a spike, almost like a denial of service attack, but accidentally created by your own system. So how do we fix this? We use exponential backoff with jitter. Let's break that down. Exponential backoff means if reconnect fails, wait longer next time. Jitter means add randomness to the wait time. So instead of everyone reconnecting at once, clients reconnect at slightly different times. So the storm becomes a smooth trickle, very important design pattern. So yeah, once you combine all of this, you realize WebSocket scaling is not just about connections. It's about architecture, coordination, and failure handling. And honestly, this is where real distributed systems engineering begins. Alright, so now let me give you the complete decision guide for real-time technologies. Because honestly, one of the biggest mistakes engineers make is using the same technology for every real-time problem. And that usually creates unnecessary complexity. Different use cases need different tools. So let's go through 7 common scenarios and what I would recommend for each one. Alright, first scenario. Chat applications and instant messaging. Things like Slack, Discord, WhatsApp, internal team chat systems. Here, the answer is very clear. WebSocket. Why? Because chat is fully bidirectional, meaning both sides continuously send and receive data at the same time. You type messages, you receive messages, typing indicators appear, read receipts update, everything is happening simultaneously. And WebSocket is built exactly for this kind of low latency two-way communication. Honestly, there is no better choice here. Second scenario, multiplayer games and collaborative editors. Things like Figma, Google Docs, browser-based multiplayer games. Again, WebSocket. And honestly, like even more strongly here, because now we need extremely low latency, sometimes under 5 milliseconds. We also need continuous state synchronization. One user moves a cursor, everyone else immediately sees it. One player moves, everybody's screen updates instantly. That kind of real-time synchronization is exactly what WebSocket excels at. Third scenario, live notification feeds. For example, your order was shipped, someone liked your post. Build deployment completed. Now here, we usually don't need the client to constantly send data back. The server mainly pushes notifications one way. So in this case, a server-sent events, usually called SSE, is often the better choice, because SSE is simpler than WebSocket. It also has built-in automatic reconnection support, and honestly, for one-way event streams, SSE works beautifully. Now fourth scenario, stock tickers and live dashboards. This one depends a little. If the dashboard is only displaying incoming updates, maybe stock prices, analytics metrics, monitoring graphs, then SSE is usually enough because data mostly flows one direction, server to client. But if the client also needs interaction, maybe changing filters, subscribing to different stock symbols, changing dashboard settings dynamically, then WebSocket may become the better option. So here, the key decision factor is data direction. One-way updates, use SSE. Two-way interaction, probably WebSocket. Now fifth scenario, AI response streaming. This is extremely common now. When tools like OpenAI, Anthropic, or Google stream large language model LLM responses token by token. They typically use server-sent events because again, data flows mainly one direction. The server streams generated text to the client continuously. Very clean fit for SSE. And honestly, This has basically become the industry standard for AI streaming APIs. Now, sixth scenario, legacy environments or corporate networks. And trust me, this is very real in enterprise systems. Sometimes WebSockets simply fail. Corporate proxy at firewalls, old infrastructure, they can block or interfere with WebSocket connections. So in these situations, long polling becomes your fallback option. Long polling is older, less elegant, but extremely compatible. So many production systems automatically fall back to long polling if WebSocket connections cannot be established. Very practical strategy. Now, final scenario. Internal microservice streaming, meaning backend services talking to other backend services. No browser involved, no front-end users involved. Here, gRPC bidirectional streaming is usually the strongest option. gRPC stands for Google Remote Procedure Call. It gives very high performance, strong typing, and HTTP/2 multiplexing, meaning multiple streams can share one connection efficiently. This is ideal for service-to-service communication inside modern distributed systems. Very fast, very efficient. So yeah, honestly, this decision table is extremely useful in real engineering work. I would genuinely recommend printing something like this or keeping notes somewhere visible, because every time you design a new real-time feature, you should consciously ask, what communication pattern does this actually need? One-way, two-way, browser support, low latency, corporate compatibility. Those questions help you choose the correct technology instead of over-engineering everything with WebSockets. Alright, so here is your action item for this lecture. And honestly, this is probably one of the easiest and most fun exercises in the entire course. You can literally start in less than 5 minutes. So first, open your browser developer console. In Chrome or Edge, you can press F12 or right-click and click Inspect, then open the console tab. Now type just 3 simple lines of code. First line, create a WebSocket connection. Something like const ws equals new WebSocket using a public WebSocket echo server. Basically, an echo server simply sends back whatever message you send to it. Second line, set the onMessage handler, meaning when the browser receives a message, print it to the console. So basically, whenever data comes back, show it. Third line, send a message. Maybe something simple like hello real time, and then hit enter. That's it. You will actually see the same message come back instantly from the server. And congratulations, you just used a real-time WebSocket connection with only 3 lines of code. Pretty cool, honestly. And the best part is, WebSocket support is already built directly into every modern browser. You don't need extra libraries. You don't need complicated setup. You can literally experiment with real-time systems right now. Now here's where things become even more interesting. Open the Network tab in DevTools. DevTools means developer tools inside the browser. Watch the WebSocket connection get established live. Then click on the connection. Switch from the Headers tab to the Messages tab, and now you can actually see individual WebSocket frames being exchanged in real time. Honestly, this is one of the fastest ways to build intuition for how real-time systems actually work under the hood. Now after that, I want you to think about your own system, your own projects. Find one feature that could benefit from real-time communication. Maybe notifications, maybe a live dashboard metric, maybe a live count somewhere, maybe chat messages, anything that currently requires users to refresh the page manually. Then ask yourself, which technology would make the most sense here? WebSockets, server-send events, SSE. Long polling? Use the decision framework from the previous slide, because different use cases need different solutions. And then finally, write an ADR. ADR means Architecture Decision Record. Very simple structure. First, context. What problem are you solving? What are the requirements? Then decision. Which real-time technology did you choose and why? Then alternatives. What options did you consider and why did you reject them? And finally, consequences. What benefits do you get and what new complexity does this introduce? Because every architecture decision always comes with trade-offs. Always. And yeah, with this lecture, section 3 is now complete. You now have a really strong practical foundation in API design. Honestly, at a senior engineer level, you've covered protocol selection, API gateway patterns, versioning strategies, consumer-driven contracts, And real-time communication systems, that's a huge amount of real-world engineering knowledge.
Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.